Okay, let's get started. So we were discussing PCA last time, and we saw that, maybe we'll start with the pictures. What PCA does is if you have a data set of points in some space of dimension D, D features, for example, and you want to come up with a representation of those data samples using fewer dimensions, such as 2 or 1, PCA gives you a way of doing that. And the way that it works is essentially you first remove the mean of your data samples, after which we call them x tilde. And then you approximate x tilde using a matrix B and a vector Z of shorter length. So this has dimension D, whereas this has dimension R, and you can choose R. The smaller you make R, the worse the approximation, but the smaller the coefficients that you represent your data set with. So here we had a picture. When you use R equals 2, what it's doing is it's finding the best two-dimensional plane, best in the sense of looking at the distance from the original samples to that plane and minimizing that sum squared distance. On the other hand, if you wanted to shrink your data down to one dimension, then you would come up with this one-dimensional hyperplane, which is just a line in your data set. And once again, it's going to choose that line so that the projection errors are minimal in sum squared distance. And then the details we saw as to how exactly this is done. We need to compute the matrix B and the vectors Zi from every x tilde I. And the way we do this is we choose B as the principal R eigenvectors from our sample covariance matrix Q. This covariance matrix Q is constructed like that. And then the coefficients Zi are just you take your full dimensional x tilde i's and you multiply them by that same matrix but transposed. So that's how you get your approximation coefficients and the approximation basis. And so what we'll do today is we will derive why exactly we have these solutions. And then we'll look at some examples of PCA with images. Any questions on the kind of high-level PCA stuff until now? Okay, so let's look at the derivation of PCA. So basically, you have a two-step derivation. The first step is to optimize the coefficients Zi for any fixed basis B, and then plug in that solution so that we now have an expression that is only a function of B, and then we'll optimize the basis B. So the first step is super easy. Let's come back to our RSS. Here's the optimization problem. We want to, for any fixed B, we want to find the Zi, the set of Zi's that minimize this sum of Euclidean norms squared. And if you look at this actually decouples over each I. So if I want to minimize, for example, Z1, then because this sum is like a term with Z1 plus another term with Z2 and so on, I only have to worry about that term with Z1. So in other words, if I want to optimize Zi, then I can ignore this and I just optimize this quantity over Zi. Okay, so that's what we have here. I want to optimize this over Zi. But if you think about it, this is exactly the same problem we saw back in Unit 2. The only difference is we had a different notation there. So there we had y minus a times beta. But otherwise, mathematically, it's exactly the same problem, and we know how to solve it. We can find the optimal zi or the optimal beta basically as this expression. Okay. So that's the easy step. The rest of it is a little bit more complicated. Any questions on this first step? Okay, so this basically means like for any matrix B that you choose, the optimal zi, the coefficients to describe x tilde I for that B will be this expression. Okay, so let's come back to our RSS expression. This was zi, and so now we plug in this expression for zi, and the result is a new expression for what we want to optimize that involves only the B coefficients. But as you can see, it's a little complicated because B appears 4 times inside a matrix inverse and so on. So this is why it takes a little bit of work to figure out what is the optimal B. So very first step is let's write this rather than having 2 xi tildes, we will write this as I times xi tilde, and then we'll have one matrix times xi tilde inside that norm. And we're going to give this matrix a name. This is going to be called P sub B perp. And this is an example of an orthogonal projection matrix. So let's talk about projection, or orthogonal projection. So I'm guessing you guys have seen this in prior classes, but let's review it. So if you have a vector x and you have some subspace that you want to project, or you want to find the closest approximation of x in the subspace, then essentially you can write that as this, where the approximation error is perpendicular to the subspace. So let's think about why that is. So imagine I start with x, and centered at x, I put a small ball there, a sphere. And I keep blowing the sphere up larger and larger until I get to the point where it first touches the plane. So at that point, I have, sorry, it's kind of a bad drawing, but I have a sphere that touches the plane exactly here. And so now, based on that, I think sorry, this is actually really, really terrible drawing. Let me try to do a little better. Okay, so we have the center of the sphere. This is the bottom and the top. Okay. So now you can see the orthogonality because any other point on the plane, right, is going to be at a larger distance from here, right? Because to reach those, you would need a larger sphere, right? So this point, which is just this point is going to be definitely the closest to here compared to any other point in this plane. I think that makes sense. And now, if you think about it, there's going to be a right angle between this vector and the plane, because maybe I'll just draw a one-dimensional case. If it wasn't at a right angle, that means that there's actually a closer point that you could have found, right? Because that's going to be closer. So basically, I don't know if this is convincing, but this closest point in the plane to here is going to be at a right angle to the subspace that you're approximating into. And so that's where we get this idea of the orthogonality. Okay, so in this particular problem, the plane, which is a kind of a subspace, is actually the column space of the matrix B, which is the set of all linear combinations of the columns in B, just that collection of vectors. So here you have B multiplied on the right by a vector Z that is going to come up with different linear combinations, and here we are allowing all possible Z. And when you think about this, if B will be, B is going to be like some set of linearly independent vectors, and now if you consider all possible linear combinations of them, that's going to fill out this plane. Right, so this is the plane that we are talking about at this point, and we are talking about an orthogonal projection, and actually there's, okay. So I'm not using the tildes on this page. I'm just saying we have some vector x, and we want to come up with the closest point in this subspace, this column space. We know that we can write x as the approximation, which is the x hat, plus the error. And we know that x hat will be in the column space, and the error will be perpendicular to the column space, based on these ideas. Okay, so this is what we call the orthogonal projection of x onto the column space. It's the closest vector to x, and we can write that in this way. So is that making sense so far? Any questions about that? Okay, so now you might ask, well, how do you actually compute that vector? Turns out you can compute it by multiplying x by a matrix, which is this projection matrix. And you can actually get E by multiplying x by a different matrix, which is sort of the partner. This is the projection matrix. This is its orthogonal complement. And the way that you construct these matrices is PB has this form, B times B transpose B inverse times B transpose. And then PB perp is just I minus PB. Okay, so that's how we actually get these X and E vectors. And there's really only two mathematical properties of these projection matrices, which are that they are both symmetric and idempotent. So as we remember, symmetric just means that the transpose equals the original matrix. I don't think we've talked about idempotent, but this means that if you square PB, you get back exactly PB. So it's like once you apply PB through a matrix multiply, if you apply it again and again and again, nothing changes. That's sort of like saying if I take a point x and I project it into the plane, and now I have this x hat, and if I project x hat into the plane, nothing changes because x hat is already in the plane. So it's like multiplying a vector by PB is the same thing as multiplying by PB squared or PB cubed or PB to any power. Okay. So those are really the two key properties of orthogonal projection matrices. Any questions on that? Yes?
So this PB orthogonal, the error, it's the same as we defined before, the I minus this.
Yeah, exactly. Did you see it?
Yeah.
This one, yeah. So, okay. So this part is PB, and then the I minus that is PB perp. Right.
And the small e, it's all of this multiplied by x.
Yeah, so if you start with a vector x, and you want to approximate it in this column space of matrix B, you just compute the projection matrix 4b, and then you multiply it by x. Or if you want to get the projection error, it's like I minus PB times x. It kind of makes sense, right? Because of this I, these two things together add up to x. Okay, so how many of you guys have seen projection matrices before? Okay, great. They definitely show up a lot, but depending on what you study. Okay, so that's the idea behind orthogonal projection. And one other fact that we won't prove, but this is kind of useful, I know, I find it useful, is that when you look at the eigenvalues of PB, you'll find that, and remember, B has R columns, and we're assuming that all these columns are linearly independent. So if B has R columns, then when you look at the eigenvalues of PB, exactly R of them will be equal to 1, and all the other ones will be equal to 0. And then because of this I minus property, when you look at the eigenvalues of PB perp, we'll have R at 0 and all the other ones at 1. Because together they give you identity. Okay, so that's that will come in useful later. All right, any questions on orthogonal projection? Okay. Okay, so how does this manifest in PCA? Well, we saw this expression before. We had rewritten RSS as sort of the sum of the squared Euclidean norms of this matrix PB perp times x tilde I. And now we realize that what this is doing is it's just computing the approximation error of x tilde I in the subspace spanned by the columns of B. So that's exactly, these are our projection errors for the ith point. And so now when we look at this, a picture like this, all of these are basically the projection errors for different i's. This is the column space of B, and these are like the original, this is the original X in the three-dimensional space, and so, for example, this here would be X hat, and then this will be your EI. Sorry, so I should put I here. Okay, so is that making sense? And so now we basically want to minimize the sum squared Euclidean distances of those EIs. I guess I should have underlines on all of these. Okay. Okay, so that's what PCA is trying to do. And now let's try to figure out the linear algebra as to how to actually do this. So there's a few steps, but none of them are very difficult. So we start with, basically this expression. It's here. We'll just give it a name. This is the cost of this matrix B. And the first thing to remember is that if you have a squared norm, let's say I have a vector A squared, I can also write that as A transpose itself. Right? So when we have this thing, norm squared, we can write that as this times itself transposed. Okay, so now we've gotten rid of the norm. Next, we remember that this transpose does nothing because that's a symmetric matrix, so you can imagine getting rid of that. And then because it's idempotent, multiplying PB times itself is the same thing as just PB perp. Okay, so we have the simplified expression here. And now, as I think we've done before in this class, we can start playing games with the trace. So if you remember, the trace of a matrix is the sum of the diagonal elements in the matrix. So this vector here, or this matrix is actually just a scalar. We have a row vector times a square matrix times a column vector, which gives us a scalar. So the trace of a scalar is just that scalar. So basically we can sneak in the trace here without changing anything. But the reason why we often do this is because the trace has this interesting property where if you have a product of two matrices in the trace, then you can swap their order, which is not something you can usually do in linear algebra. So now that the trace is there, we can swap the order of those two matrices. Technically, they're actually both vectors, but we're thinking of vectors as examples of matrices here. So this is going to allow us to move this one over here. Or actually, what we're going to do is we're going to move this one over here. So that will give us this. And now because the trace is a linear operator, the sum of the trace is the same as the trace of the sum. And so we can move the sum inside, and we can actually move the sum through this PB because matrix multiplication is also linear. And finally, we get the sum of I over these outer products. So this is like a column times row, which, as we know, is a whole matrix. And in particular, this is a familiar matrix. If we sneak in a 1 over n here and then compensate with an n over here, then we recognize this as just the sample covariance matrix of our data. Okay, so to summarize, our cost, the thing we're trying to minimize, is n times the trace of PB perp times the sample covariance matrix. Okay, so any questions so far? Okay, so the sample covariance matrix has an important property, which is that it is positive semi-definite. So if you remember, what that means is that for any vector x, if you form this quadratic, if you make this quadratic form using x, this scalar will be non-negative no matter what x is. Okay, so this is a property of the sample covariance matrix, and let's prove it. So let's start with this expression here, where x is arbitrary, and then we substitute in q, which we know by definition looks like this, and then we can move this, we can move the sum, or the averaging out due to linearity, and then we have the average of this times this, but these are both scalars, and actually you can see that they're also just transposes of each other, and because a scalar transpose is identical, these are really the same thing. So we can just use this squared, scalar squared. And now when you think about it, if you have the average of some scalars squared, there's no way that could ever be negative. So this is definitely going to be greater or equal to 0. Okay, so now we know that this matrix, covariance matrix Q, is positive semi-definite. And the reason that that matters is that when you take the eigendecomposition of a symmetric positive definite matrix, it has a very special form. You can write it like this. And this matrix V is an orthogonal matrix. It is square. All of its columns are unit norm. All of its rows are unit norm. All of its columns are orthogonal to each other. They're mutually orthogonal. All of its rows are mutually orthogonal. So because of that mutual orthogonality, you get this property, or if you swap the transposes, you get this property. And so this one tells you that the rows are orthogonal, and this one tells you that the columns are orthogonal mutually. And then this lambda matrix is a diagonal matrix of these composed of these scalars, and these scalars are all going to be real numbers, and even more, they're going to be non-negative. So those are special things that happen with symmetric positive definite matrices. If you have a generic matrix and you compute its eigendecomposition, it may actually involve complex numbers. The symmetry is what gives you these real numbers, and this positive definite property is what gives you the positive semi-definite property is what gives you this non-negative aspect of it. Okay, so now we have this very important structure for our covariance matrix, and we can examine how that plays a role in here. And we'll also make one other assumption, which is that our eigenvalues are sorted from large to small. So most eigendecomposition solvers do not do this for you, but you can always do this as a final step. You can compute an eigendecomposition, and then you can sort the eigenvalues from big to small, and then what you do is you just swap the columns in V correspondingly. And so then you will have this sorting property too. Okay. Any questions on the eigendecomposition stuff? Okay, great. So this is what we finally have then. We have the problem that we have translated down to is we want to optimize B, which is basically parameterizing this orthogonal projection matrix. And then here we have Q, which is this symmetric positive definite matrix. And it was proven back in 1936, 90 years ago, that the B, or at least one of the B's that solves this, are going to be the R principal eigenvectors of this Q matrix. So that means that it's the first R columns of V. And actually, it's a bit more general than this. You can take, you could, for example, you could shuffle the columns around. That would also work. You could even, you could scale these. You could do linear combinations of them. As long as whatever B you choose, we'll call this, B hat, as long as that has the same column space as this. So any B hat will work that has the column space of this. But most people just choose it as those principal eigenvectors themselves. They're unit norm, they're mutually orthogonal, so they're pretty convenient. Okay, so our next step will be to prove this result. Are there any questions about where we are? Okay. All right, so there's different ways to prove this. I think this is the easiest one that I've seen. So this is our objective, this is our cost. We would like to minimize this over B. So the first thing we can do is we can write this orthogonal projection matrix as I minus the regular projection matrix. And then we can use the linearity of trace to write this as two terms, n trace q minus n trace pbq. And since we're optimizing over B, this term doesn't really matter. And in fact, what we're doing is we're minimizing this cost over B. And now you can see that if I maximize this trace term over B, that will minimize the cost. So let's think about this trace term as a utility rather than a cost. Call it U of B. And we want to maximize this guy. Okay, so this is the problem we have. So now let's use our eigenvalue decomposition. We'll plug in Q. And now let's use this trace property to move this VT to the front. Okay, and let's think about what we got. So we have a matrix here, which is just going to be some matrix. And then we have on the right is going to be another matrix which we know is diagonal. And at the end of the day, what we're doing is we're taking the trace of this times this. So if you think about what happens in this trace, so this matrix multiply basically causes this first diagonal element will multiply this column, the next one will multiply this column, and so on. But then you're just taking the trace, which is of those scaled columns, you're only taking the diagonal elements and summing them together. So that means that all these other terms in this matrix play no role in the trace of this. So the only ones that matter are the diagonal elements of this matrix and these scaling values. And so if we define alpha j as the jth diagonal entry in this matrix, then this final thing is the sum through the trace of that alpha j times the lambda j, like this. Okay, does that make sense? All right, and so now, okay, what about alpha j? This is kind of a complicated way to write it. A simpler way to write it is rather than taking the full matrix V and then making a matrix and extracting the jth diagonal element, let's just look at the jth column of V here and here, which is going to be Vj transpose in Vj. And this actually just gives us that scalar value directly. Okay, so now we have an expression for these alpha j's and an expression for our utility function. Okay, so to make this easier, there's actually a couple important properties of alpha j that we can deduce. So let's look at the first one. So we know that this is one expression for alpha j, but we also know that because of the idempotent and symmetry property, we can rewrite PB like this if we want. And once we write it like this, now we have this times its transpose, which we can write back in the form of a norm squared. And now a projection matrix always shrinks a vector. It can never expand a vector. And so basically the projection norm is always less than or equal to the vector before you took the projection. And because these are orthonormal vectors, we know that the lengths of those are 1. Also, we know that this is non-negative. So that means that the alpha j's must be somewhere between 0 and 1. Okay. Any questions on that? Second thing, let's look at the sum of the alpha j's. Okay, so the sum of the alpha j's is basically just the trace of this matrix, because those are the diagonal elements. And again, because of the trace property, we can move V to the front. And then once it's in the front, we know that because it's an orthonormal matrix, this is identity. So we get this. And now we can expand this into its expression, the projection matrix. Once again, because of the trace property, we can move B transpose to the front. And now, because the columns of B are linearly independent, this matrix is invertible, and it times its inverse is going to be identity matrix of size R. And the trace of that is just the sum of the diagonal terms, which are all 1, and there's R of them. So finally, at the end of the sum of the alpha j's is equal to R. Okay, so to review these alpha j's that we are trying to optimize, these are the things that depend on, they're affected by the matrix B. They're numbers between 0 and 1, and they have to sum to R. Okay, so to rewrite this optimization problem, find the alpha j, these R terms alpha j, as numbers between 0 and 1 that sum to 1, that maximize this quantity for some fixed set of lambda j's. Okay, so this is a problem that you can actually solve intuitively if you reformulate it into things that maybe you do in your daily lives. So let's say you're going to the store and you must buy R pounds of food total. So basically alpha j is how much, the weight of the jth food that you will buy. So you have to buy R pounds total, And for each food, you can buy between 0 and 1 pounds. Maybe the store only has 1 pound of every food, so that's the most you can buy. Now let's also say that you have your favorites among these foods. And so the lambda j is basically, you could say that's lambda j units of enjoyment per pound of food j. And your objective is to maximize your total enjoyment, right? This is enjoyment per pound of jth food. This is how many pounds you buy of it. This is your total enjoyment for what's in your shopping cart. So given that, what do you think you do? You go to the store, you have to buy our pounds of food. They have 1 pound of all these different foods. Some you like, some you don't like. How are you going to spend your money?
Start with the one you like the most, get that, and then...
Yeah, exactly. So you're going to pick 1 pound of each of your favorite foods until you have R of them, right? That's exactly the solution. So that means, in terms of your alpha j's, the optimal alpha j's, 1 for the, j, remember j is sorted from large to small, like your enjoyment goes from large to small. So you're going to, for the j equals 1 through R, alpha j is 1, and then for the remaining j, not going to buy any of that food that you don't like. Okay, so we've now solved this optimization problem. So now we just need to kind of go backwards and figure out, okay, if those are my alpha j's, what are the vj's that correspond, or what's the matrix B that corresponds to that? So, okay, so this is one way we could do it. So I'll just say, like, if you do this, I'll show you that the alpha j's work out. So let's say you set B equal to VR, where VR contains these R principal eigenvectors. If that's the case, then PB, as we know, is just B times B transpose B inverse B. And so now we plug in B equals VR here, and then we make some simplifications. Because these columns are orthogonal, mutually orthogonal, this gives us identity, after which we have this. And so if PB is this, then the alpha j's, which were defined this way, remember that Vj is going to be the jth term in this, the jth row in this matrix. So when you multiply this Vj times this matrix, you'll get basically a 1 at the jth entry and otherwise zeros, because all the rows are orthogonal, mutually orthogonal, and this is the jth row. So basically, so these alpha j's turn out exactly the way we want if we choose B in this way. Okay, so finally, this is basically we've proven this Eckert-Young theorem. So now we know exactly how to set B at this VR matrix, and from step 1 in our proof, the easy step, we now know also how to compute the coefficients with that B. So this is going to be VR transpose, those turned into identity, and now we have VR transpose xi tilde. So that's the solution we saw earlier. Okay, so just to summarize everything, you're given data, samples xi, you can compute their sample mean, and then what you're going to do now is you're saying, I'm going to approximate the ith xi as a sample mean plus some deviation that depends on I, and that deviation is expressed in some sort of basis, which I construct using the principal eigenvectors of my sample covariance matrix, and the coefficients, which I compute this way, again, using those principal eigenvectors. Another way we can write this, if you like, is we can write it like as a product of this. This is like your data matrix, but you've removed the mean from every column. So these are your rows, your mean removed rows. And then here we have the transpose of that. And so now you can see that this is going to be this outer product. It's going to be this times this plus the next one times the next one plus the next one times the next one, exactly as this says. Okay, and this will be useful in the next, what we talk about next. Okay, so to summarize it, we know what PCA does, we know exactly how to compute it, or we know at least at a high level how to compute it. We'll next talk about a more efficient way of computing this. All right, any questions so far? Okay, a lot of linear algebra today. Okay, actually the first thing to talk about is performance. So we know how to compute PCA, but we would like to know basically how to choose that rank. And we know that as we choose larger ranks, we get better performance, but less compression, more coefficients. So to be able to choose R, we have to know how much performance we're losing for a given R. So if you think about how we did this back when we studied linear regression, and it's kind of like scalar linear regression in that we only had scalar targets, we use this quantity called R squared. Now, don't confuse this R with this R. This is our math italicized R, whereas in scalar linear regression, this metric used a non-italicized R squared. That's just the traditional statistics, how they call it. And we remember that to compute this, it's 1 minus RSS over n times sy squared. So for PCA, we're going to do something almost identical. We're going to use something called proportion of variance, which has pretty much the same form. The only difference is that rather than the target variance, because we have no targets now, we have the total data set variance. So Q, if you remember, Q is like our covariance matrix. The diagonal elements of this are the variance of every entry. And now we're just taking the sum of all the variances. So this is like the total variance of our X data set, whereas this is the total variance of our targets, the things we're trying to predict. Okay. So this is how people measure performance of PCA. Any questions about this? Okay, so now let's see tractably, how does this relate to the eigenvectors, eigenvalues? Let's look at this denominator. So n times trace of q, well, let's plug in our q eigendecomposition, v lambda v transpose. We know that I can move the v transpose to the front, after which point it gets canceled by v. So now we have just n trace of lambda, which is just n times sum of our eigenvalues. And notice we are summing all of them here. What about the RSS? So the RSS was, we deduced earlier that this is n times the trace of PB burp Q. And earlier we had split this, we had written this as I minus PB, that allows us to split things this way. And so now this first term, we just derived this. And what about this other term? Well, if you go up earlier in our derivation, we figured out that this is the sum of the eigenvalues only up to R. So we have two very similar terms, but one of them has sum up to D, the other sum up to R. R is usually less than D, can never be more than D. So essentially what we're doing here is this sum is subtracting the contribution from the first R terms here, leaving the remaining terms. Okay, so that is what RSS is and the denominator. And now let's come back to POV. Let's rewrite 1 in a way that allows us to, has the same denominator here. So we'll write it as this over this. And over here we have this term, and here we have this term. And now you can see that they have the same denominator, so we can write the answer as this, and then we just have to subtract the numerators. Well, this is the sum over all the terms. This is minus the sum over the last terms, which gives us the sum over the first terms. So numerator and denominator are similar, except the numerator only goes up to R, whereas the denominator goes through all your eigenvalues up to D. And just like in linear regression, we want this quantity to be as close to 1 as possible. It's always going to be a number between 0 and 1 in this case. Okay, so any questions on POV? Okay. Great. So we kind of have the basics of PCA covered. The next thing to talk about is a faster way of computing it. How many of you guys have heard of the singular value decomposition, the SVD? Okay, so this is one of the most useful decompositions in linear algebra. There's many, many decompositions you may have heard of in linear algebra. There's eigenvalue decomposition, QR, LU. There's just many, many, many decompositions. But most of the decompositions only apply to a subset of matrices, like the matrix needs to be square or something like that. Whereas the SVD you can apply to any matrix no matter what, so it's very useful in that sense. And what it does is it decomposes any matrix X into a product of 3 matrices. The first is orthonormal, the last is orthonormal, and the middle one is diagonal. So one way to interpret what X is doing, what this SVD is doing, is it's saying, like, if you think about X as an operator, so let's say I have a operator acting, I don't know, maybe on some coefficients beta, I can think about that as actually like 3 matrix operations composed together. I take my beta and I first multiply by this orthonormal matrix. Well, an orthonormal matrix, all that does is rotate the vector. It never changes its length. So it says you start with beta and you rotate it. Next, you go through, you multiply it by a diagonal matrix. All that does is scale the individual coefficients because it's diagonal. And then you go through another rotation. Okay, so basically it says that any linear operation, you can think of it as 3 operations: rotation, scaling, and another rotation. You can, any linear operation, any multiplication by matrix X of whatever size, you can always think about it that way. So that's that's maybe one way to interpret it. And this often helps with, if you ever want to prove something in linear algebra, you plug in the SVD and all of a sudden things start simplifying and things start making sense. So let's try to visualize a little bit about how these matrices look. So there's different cases. So if X is, for example, tall, then the SVD looks like this. So these U and V matrices are always square. And S always has the same size. Sorry, this one. They always have the same size, S and X. So in my picture, whatever size of X, that's the size of S. And then the square matrices just have to match the dimensions of S. So that would be what we have if, let me also make this diagonal. So this is a diagonal. So that you only have those entries. That's for a tall X. Now what if you have a wide X? So wide X, you need a small square matrix, an S matrix that has the same dimension as the input, and then a big square matrix. So here, diagonal. And if X is square, then it's square times square times square. Okay, so the other important thing about the S matrix is that the coefficients are non-negative and they're sorted from big to small. Now, in this formulation, you can have some of them equal to 0. So another way that I could draw this, for example, is maybe like this, to emphasize that maybe some of those singular, these are called the singular values, the little s's, a few of them could actually be 0. So that means that the only non-zero elements are just those. So just to summarize, we have this decomposition into orthogonal, orthogonal, diagonal, and yeah, the dimension of, the smallest dimension in this problem is, the minimum of those two dimensions. And finally, all of these guys are non-negative, sorted, but they could be equal to 0. Okay, so that's the standard SVD. Now, there is an economy SVD, which exists because if you think about it, if you have a bunch of 0 elements here, then what that means is that when you do this multiplication, all those columns are all zeros. Those will pretty much cancel the effect of any coefficients there, because they'll just be multiplied by 0. And they will cancel the effect of, all of these coefficients will cancel the effect of those. So when you compute these big square U and V matrices, you end up computing a whole bunch of coefficients, maybe which are not relevant to how you construct this. They're just constructed so that they are mutually orthogonal with each other and with the columns that matter. Okay, so there's this economy SVD that computes only the coefficients that matter. So for example, for this one, it might look like, so here you're going to have tall U matrix, small diagonal matrix, and a wide V transpose. So this dimension has to match this one, this dimension has to match this one, and importantly, this S matrix is constructed so that the smallest element is positive, meaning this S is invertible. It's square and invertible. Let me write an example of a wide one. Well, the wide one might look like this. Okay, so you can always compute the SVD for any matrix, and it's really useful to break matrices down into these building blocks for proofs, or as we'll see, for some computations like PCA. We do have some properties like these, but we cannot swap. We cannot swap the order anymore. So for example, this U, it might be a tall matrix. Its columns are mutually orthogonal and normalized, but if I do the outer product of two tall matrices, I definitely don't get identity. Okay. Okay, any questions on these SVDs? Yes.
So, like, in real life, in Python or something, if I'm calling an SVD function, it's going to do this economy one, never the...
Oh no, you have the choice.
Oh, cool. Okay, cool.
Yeah.
Okay.
So here it is in Python. So full matrices equal false. That, I don't remember if that's the default or not, but you can just put true or false here, and you force it to do what you want. And then what it returns these three quantities, which is the U matrix, the S vector, so that's why I made it small, and the V transpose matrix. Different in MATLAB, you would get U, you'd get an S matrix, and you get the V without the transpose. But in Python, or at least in NumPy lineage, it's this way. Yeah, sure. So, well, I think that's a good time to stop. So what we'll do next week is we'll show how the SVD gives us a quick way to compute PCA, and then we'll have a more fun lecture looking at a lot of pictures and stuff. No linear algebra. So, all right, we'll see you guys on Monday. Have a good weekend.